Hello everybody. I would like to give you a few insights in, let's say, what are the important aspects in the design of the conductive mass for lithium-ion battery electrodes. Let me allow a few words about Imerys Graphite Carbon. We are actually the carbon division of Imerys Group. We have basically production for conductive carbon black that we produce in Belgium. We produce natural graphite in Canada and in Namibia, synthetic graphite in Bodio, and we have a plant to coat graphite in the south of Japan. The division has about 500 people. We have about 30 R&D people in 2 locations, one in Switzerland and the other R&D center is in Japan. We are basically a company. Okay, we consider us today as a one-stop shop for carbon, as we produce natural flake graphite, synthetic graphite, carbon black, and also silicon composites, with controlling also the resources, so that we have a security of supply that we can offer innovative solutions coming out of our R&D laboratories, and possibility to customize based on, let's say, customer request. So this is a scheme showing the electrochemical lithium-ion cell. So we have the positive electrode with the current collector, the negative electrode, and you see here schematically drawn where carbon materials can be found. In the negative electrode, basically as the active material, together with some conductive graphite, carbon black, and we talked about the nanotubes as well. And in the positive electrode, basically as in the conductive mass, where basically conductive graphite, conductive carbon black, and nanotubes are used. I will focus here a bit on, let's say, how to leverage the complementary properties of conductive carbon black, carbon nanotubes, graphite, and multi-layer graphene to tailor multi-component conductive additives that are important when designing the conductive mass in lithium-ion batteries. So the slide here shows some information about the electrical resistivity of lithium cobalt oxide electrodes and LFP electrodes as a function of the carbon amount when basically mixing in graphite and conductive carbon black in the electrode mass. So what you can see here, basically, you have this kind of percolation threshold where with increasing carbon amount, the resistivity percolates from a high resistivity level into a lower resistivity level. And what can be seen here basically is that with carbon black, this critical volume fraction, where basically the percolation threshold occurs, happens at lower carbon amount versus graphite, whereas with graphite we can reach lower ultimate resistivity levels when increasing the carbon amount to higher level. And this is basically the same in LCO and LFP. What I show here is basically the electrical volume resistivity of pure graphite and carbon black. So what we used here is a kind of die-type arrangement where the sample is put between 2 electrodes, and that also acts as kind of piston to compress the sample. And we measure, basically we apply a force and an incremental pressure on the sample, and by basically measuring the resistance between the electrodes, we can calculate the resistivity from the electrode area and the height of the sample. So what you basically see here is the electrical resistivity of pure graphite and carbon black. And interestingly, you see for the carbon black very basically the same behavior. So when increasing the pressure, you basically densify the sample at a relatively low level of density and you can see that the electric resistivity sharply drops when the density, when the pressure is increased, when the density of the sample is increased, whereas in the case of graphite, you have to watch here for the table. You basically see that the electric resistivity is at a lower level, and the density is increasing significantly, whereas the resistivity is not improved significantly when increasing the pressure when increasing the pressure of the sample. This slide here shows the mechanical work that can be calculated as from the sum of the incremental pressure increases and the volume changes that happen. So basically, you see here in the case of the carbon black materials that we tested, that the mechanical work sharply increases when increasing the pressure and let's say at a relatively small density range, whereas in the case of graphite, the material can be densified with relatively low amount of work. So what you see here is basically that the graphite shows a significantly higher compressibility that basically can be used when working with mixes of carbon black and graphite in the electrode mask. This here shows NMC electrodes with a 2% of conductive carbon mass. And what you see here with regards to the electrical resistivity, you see how the resistivity is changing when replacing part of the carbon black by graphite. So up to 75% of graphite, basically the electrical resistivity remains at a relatively low level, and then there is a sharp increase when going further. And at the same time, if you see the electrode density, is basically increasing when putting in graphite in the conductive mass. So at about 1-to-1 ratio, there is a significant increase of the density that can be achieved at the same pressure applied. And so this looks to be a sweet spot that can be used when on the one side a sufficient electrical conductivity needs to be achieved, and at the same time the electrode density has to be maximized at a given pressure. This is translated, of course, in the specific charge and charge density. It shows the slide here shows cyclic stability of NMC electrodes containing pure carbon black and mixes of carbon black with graphite. And of course, the specific charge is not changing, whereas due to the compressibility of the graphite component inside the electrode, by being able to densify to a higher level, the charge density that is achieved for the electrode can be improved significantly. So depending on the goal of the electrode design, the two components act in a complementary way. We see also changes on the adhesion of NMC electrodes. Basically, you see here the peeling force that is measured by peeling off the electrode from the current collector. And what you basically see is that the peeling force increases when decreasing the amount of carbon in the electrode, and at the same time reducing the amount of carbon black and adding graphite. So there is a clear indication that with the increase of graphite in the conductive mass, the adhesion can be optimized. When optimizing the electrode resistance, there is always this interplay between electrical and ionic resistivity. And I put this slide as an example. You see here basically a negative electrode, and the electrode resistance of this negative electrode that is measured by measuring the direct current resistance in a symmetrical cell at 50% state of charge when applying a 1C current pulse at 20 seconds. So basically, the electrode resistance when adding graphite conductive additive into the electrode basically is decreasing and then sharply increasing. So what happens initially, the electrical resistance of the electrode is optimized, is decreased, and at a certain point of time, there is an issue with the ionic resistivity of the electrode because the conductive additive is basically put in the pores of the electrode, so the electrolyte retention is basically deteriorating, increasing the electrode resistance overall. And this is basically translated also in the high current discharge. You see here the charge retention at 2C of the negative electrode that goes through an optimum at about 5% of graphite additive amount and then sharply drops down. There is, when optimizing the critical volume fraction of the conductive additives, there is some work that was done by Spahr and Manga showing the influence of the carbon aspect ratio on the critical volume fraction, and this is basically a computational study, a simulation that basically show that the critical volume fraction can be significantly decreased by either working with very, very low aspect ratios or by working with very high aspect ratios. Very low aspect ratios would mean extremely flaky materials, and high aspect ratios would be the tubular form factors. And this can be seen basically here when looking at the in-plane electrode resistivity of multi-wall nanotubes versus conductive carbon black. You see here basically that the electrode resistivity at a given conductive mass is decreasing when switching from carbon black to multi-wall carbon nanotubes. Interestingly, with mixes of carbon black and conductive nanotubes, the electrode resistivity is not significantly changed, and this is basically, this can be found at different amount of conductive carbon additive, where you basically see that above a CMT fraction of 20%, the in-plane electrode resistivity is relatively stable. The slide here shows cyclic stability at 1 weight% of conductive mass, so this is relatively low. It's basically where the conductive carbon black already is pretty high in the percolation with regards to the electrical resistivity. And what you basically see here is that, of course, the pure carbon black shows a relatively bad cycling stability, but at the same time, when working with mixes of carbon black and multi-wall carbon nanotubes here, the cycling stability can be optimized. And again, I'm coming back to this optimization of electronic conductivity and ionic conductivity. On one side, we have the carbon nanotubes taking at this very low carbon concentration over the conductivity component. So basically the carbon nanotubes deliver the conductivity, the electronic conductivity, but at the same time, with the carbon black, the electrolyte retention is optimized. So with regards to the ionic conductivity, the carbon black component has some benefit in the electrode. And my last slide here shows our first results with single-wall carbon nanotubes, which is actually the two-wall product. So you see, especially in the area below 1 weight% of carbon in NMC electrodes, that an electrode resistivity can be achieved with the single-wall nanotubes that are basically at a lower concentration or lower conductive mass compared to the multi-wall nanotubes. What comes quite near is nano graphite, but still the single-wall nanotubes are better. And basically, if you consider a range of a certain resistivity range, what you can see here, what you can achieve with regards to the in-plane electrical resistivity with a conductive carbon black about 2%, you can achieve with the single-wall carbon nanotubes at about 0.18%. You see also on the right side some SEM pictures of the electrodes where you can see nicely how the positive electrode material particles are contacted with these single-wall nanotubes, and we can still see bundles of single-wall nanotubes, so the dispersion still, I think, could be optimized a bit more. So I would, of course, like to thank the R&D team for the measurements that I showed here, and I'd like to thank you for your attention.
Thank you very much for the detailed technical presentation with a comparison of different results. So, what is your vision in terms of future conductive additives? Should it be a combination of graphite and single carbon nanotubes, or should it be only one type of additive?
It's a very general question.
Yes.
As we can see more and more applications for lithium-ion batteries, we talk here a lot about the automotive application, but we see in the future probably also application in the range in the area of energy storage. We have the consumer application with a very, very diversified application, looking for smartphones on the one side, power tools, let's say on the other side. So all the applications have different requirements, and based on the requirements, the design of the conductive mass and the design of the electrode becomes more and more important. So I think the question cannot be answered straightforward.
I understand.
It is more than a question, what are the requirements of the different applications and which applications will grow?
Very clear. Thank you for the straight answer. There's no one answer to this question. Yes. Yeah. It's a complicated chemistry.
And what we see more and more certainly is that the design of the electrodes, especially the conductive mass, is getting more and more differentiated. Right.
Clear. Gentlemen, any other question? Yes.
Okay, I think most of the results you saw was for NMC.
Yeah.
But can you share something about the use of for graphite anodes? So.
Also there, I think the question of whether you want to use a conductive additive in the graphite electrode or not is at the end the question, what do you want to achieve? Do you want to achieve 12C high rate discharge? Do you want to achieve 1C high rate discharge? And this is basically important in the decision whether you want to use a conductive additive or not. And we had a discussion before already also with regards to using primer coatings on the current collector and so on. I mean, it's a very similar discussion. What is really wanted?
Okay.
Other questions, colleagues? Yes, totally.
Yeah. You say here the conductive graphite. So what's the difference between this conductive graphite compared to a typical graphite we use in the anode? This conductive graphite is something like thinner layer, something like graphene, or what's the difference?
Yeah, I mean, we are for sure moving from, I mean, we are talking about very anisotropic or anisommetric particle shapes. And the trend is certainly to go further in this extreme. And of course, I would say people talk about graphene today. Of course, single layer graphene, whether this can be isolated or not, I'm not so sure. For me, a single wall nanotube is basically what will happen, because the graphene layers tend to roll, so at the end you form the tubes.
This is why we call them graphene tubes. I saw it during the presentation. Actually, graphene tubes.
It is certainly an effect, right? But when you talk about conductive graphite, it is for sure a very anisommetric particle shape. Which, by the way, is completely the opposite of what you want or what you would use as anode material, right?
So this conductive graphite is like very small particles of graphite compared to the graphite we use.
Correct.
Any other difference besides this size difference?
Yeah, I mean the surface, of course, can be different, as you know. I mean, you talk if you look about a standard natural graphite anode material. Basically, most of them work with an amorphous coating that basically helps to adjust the compatibility with the electrolyte and controlling many different aspects and parameters in the cell. A conductive graphite for sure works with other ways of optimizing the surface. So it is not amorphous, it is not coated with an amorphous carbon. Otherwise you would lose the conductivity.
So if, let's say, if I apply your conductive graphite in my anode, we may have also capacity.
You have capacity like a normal graphite, yes.
It also has like 360 milliamp hour per gram.
Yeah, it's pretty high because we talk about high crystallinity graphite. So for the typical conductive graphites, you would, I mean, it depends on the current, right? But if you work with very low current, you would even get close to 370.
Okay. Yeah. So this is also the synthetic graphite, not the natural graphite, just break them into small pieces.
It is maybe less a matter of the origin, even though today we use mainly synthetic sources to produce this type of materials. And this has to do with purity and the way how purity is controlled.
So actually, then my question is that compared to the synthetic graphite, you have to break the synthetic graphite into small pieces, then you call it conductive graphite, or you have other measurements.
Yeah.
And the second question is that you said you have a multi-wall CNT, right?
Yeah.
So where did you get this from? Chinese suppliers or other companies?
We work with Chinese sources, also with European sources.
Okay. So this data is from
Chinese sources, yes.
Still, I see that the single wall is better than multiple.
This is what we have seen too, yeah, absolutely.
And as you said, if you have a single wall and the CNT and the SP, you said actually the conductive mainly comes from the CNT.
At low concentration, right? Because at the end you have percolation effects, right? So it is always the question when you are in the low resistivity level. And if you work below 1%, for carbon black you're already very in the sharp increase, right? So in this concentration range, basically the conductivity, electrical conductivity, is taken over by the nanotube component.
And the carbon black just act as you said, it's take more electrolytes.
Correct. You control the electrolyte retention in the electrode. Yes.
During cycle, they can keep maintaining the electrolyte.
Exactly, yes.